So let's discuss sequences, the definition of a sequence and the type of a sequence. Well, let's discuss the definition of a sequence first. A sequence is a function whose domain is a subset of the set of natural numbers. So basically, the first condition is that a sequence is basically a subset of the set of natural numbers. But what exactly is the subset? Obviously, there is no one sequence. There can be numerous types of sequences. So, but they all are in the subset of natural numbers. The first term of the sequence is denoted by A1, the second is denoted by A2, the third by A3, the fourth by A4, and so forth. So basically, we just simplify it down to the nth term. N can be any number. So for example, if n was 6, so the sixth term of the sequence is denoted by an, and since n is 6, the sixth term of the sequence is denoted by a6. So that's that. And what's the type of a sequence? Well, we will be able to find a pattern from the given initial terms of a sequence, and then we can deduce a rule or a formula. So basically, what this means is, if you have a sequence of numbers, they will have a pattern, and from that pattern, you can basically deduce the formula in which, when you plug in a value, so for example, if you plug in the sixth term, so if you plug in 6 into the n in the formula, it will give you the sixth term. So that's the basic overview of what a sequence is and what is a type of a sequence, and we'll get into further details later. So we basically had an overview of what a sequence is. So let's see how we can find the first 4 terms of a sequence. So write the first 4 terms of the following sequence. This is the formula. This is the pattern or the formula. So just to tell you what this really means is, it means that if we want to find, for example, the 6th term in this particular sequence, we will obviously plug in 6 in place of the n's, as n represents the nth number of the sequence. So let's see. Well, you've been given this sequence, and you'll obviously plug in 1, 2, 3, and 4, as those are the first 4 terms. So when you plug in n is equal to 1, you get 1 over 3. You'll plug in n is equal to 2, so you plug in 2 in place of the n's, and then you'll get 2 over 5. When you plug in n is equal to 3, you get the value of a3, which is 3 over 7. When you plug in n is equal to 4, you get the value of a4, and you plug in the 4's in place of the n's, and you get 4 over 9. So you have 4 values, and those are the required terms. So a1 is 1 over 3, a2 is 2 over 5, a3 is 3 over 7, and a4 is 4 over 9. So these are the first 4 terms of this sequence given to us in the question. And that's about it, really. So now we'll see how we can find the next 3 terms of a sequence when we are given the initial term. So this is the sequence given to us, and basically we've been given the value of a1, and we have to find the next 3 terms, so basically a2, a3, and a4, by using this information given to us. How will we do that? Well, these are the things given to us, and when we plug in n is equal to 2 and 3 and 4, well, what happens? So we have to find a2, which is when we have n is equal to 2. So we'll plug in 2 in place of n everywhere. So 2 a2 minus 1. So basically 2 into a1, because a2 minus 1 is a1. So 2a1, and we already have the value of a1 over here, which is 1. So 2 into 1, which is equal to 2. So A2 is 2. Now when we put in the formula for A3, so A3 is equal to obviously 3 A3 minus 1, since it's n a n minus 1, so 3 A3 minus 1. And A3 minus 1 is obviously equal to A2. So it's 3 A2. We already found the value of A2 before, which was this 2. When we plug in that 2 in place of A2 over here, 3 into 2, we have 6. And so A3 is equal to 6. And similarly for A4, we have the same procedure. We have 4 in place of the n in this sequence given to us. So the n over here will become 4. The n over here will become 4 as well. So this is 4 into A4 minus 1, and A4 minus 1 is equal to A3. So 4A3, and we already found the value of A3 before, which was 6. So 4 into 6, which is equal to 24. And now we have the three terms that we had to find, the next three terms in the sequence. So basically, the three terms are 1, 2, 6, and 24. So yeah. Now, will be required to find the seventh term of a sequence? Well, it's usually easier for us to actually find the first, if it tells us to find the first four values, or like something that is in a flow. But when we have to find an abrupt number, an abrupt value, so like we have to find specifically the seventh term of a sequence. Well, how do you deal with that? Well, we have been given in the question that the first four values, the first four terms in the sequence, and we have to find the seventh term in this same sequence. So how do we deal with this? A1 is obviously 2, A2 is obviously 6, A3 is obviously 11, and A4 is obviously 17. That is all we're given. So A1 is equal to 2. And we have to find the relation between A2 and A1, and then we have to find the same relation between A3 and A2 to find an actual pattern. So A1 is 2. So 2 plus 4 is equal to 6, right? So A2 is 2 plus 4. And A3 is 6 plus 5. A3 is 11, and 11 is equal to 6 plus 5. So basically, you can actually simplify this down like this. Draw these, I don't know, curves or arches, basically, like this. The difference between 2 and 6 is 4 plus 4. The difference between 6 and 11 is plus 5. Oops. The difference between 11 and 17 is plus 6. And now you can see a pattern between these three, 4, 5, and 6. So like, see this, A4 is equal to, A4 is 17, and that is 11 plus 6. So now you can see these numbers, 4, 5, 6. So obviously, A5 would be equal to, well, 17 plus 4, 5, 6, 7. So it would be equal to 17 plus 7. And that would be equal to 24. So, see this? Now, A6 would be, right, 24 plus 8. And A7 would be 32 plus 9, which will be equal to 41. And that is how we found the seventh term of the sequence. So, let's have another example here. We have, let's find rational, the seventh term using rational terms. But this gets a bit more tricky than it did before. Those were just simple integers. These are rational numbers. So let's see how we'll deal with this. We'll deal with this the same way we did with it before. But now the sequence, the pattern is a bit difficult to find. So let's see how we do it. We have A1, 1, A2 is 3 by 2, A3 is 5 by 4, and A4 is 7 by 8, and we have to find A7. So A1 is given to us, A2, 3 by 2. Well, obviously, it will be something like this. 1 plus 2 will give you 3, and 1 into 2 will give you 2. So that's how you get 3 by 2. Now we have to go from 3 by 2 to 5 by 4. Well, 3 plus 2 will give you 5, and 2 into 2 will give you 4. So we'll deal the numerators differently in one sequence, and we'll deal with the denominators in a different sequence. So for the numerator, you can clearly see that, well, it's being added up by 2. 1 plus 2 is 3, plus 2, whoops, plus 2, plus 2. So that's how the numerators progress. And in the denominator, well, 1 is equal to, obviously, we'll deal the 1 as 1 by 1. So to go from 1 to 2, you'll multiply it with 2. So to go from there, it'll multiply it with 2. 2 will be multiplied with 2 to give you 4. 4 will be multiplied with 2 to give you 8. So the denominator is being multiplied with 2, and the numerator is being added by 2. So A3, 3 will be added with 2, and 2, the denominator in the 2 in the denominator will be multiplied with 2. And now we have A4. So the numerator 5 in A3 will add 2 into that, and in the denominator we had 4 in the denominator here, that will be multiplied with 2. And so we'll go to A5 with the same thing. We'll get 9 by 16. A6 will get 11 by 32. And for A7, well, 11 plus 2, and in the denominator 32 multiply by 2. So 11 plus 2 is 13, and 32 into 2 is 64. And so that's the 7th term in the sequence. Now, in most cases on the basic level, you'll deal with two types of progressions. One is the arithmetic progression, and the other is the geometric progression. So let's first discuss the arithmetic progression. Now, the arithmetic progression, what is it really? If you have a sequence and it goes till an, so n is any number, so the nth term, it is an arithmetic sequence or an arithmetic progression if an minus 1. What does this mean? It means the difference between two consecutive terms. So for example, if n is 2, that means this is the second term, and obviously an minus 1 would be n minus 1 would be 2 minus 1, so a1, which is the first term, so the consecutive term, the first and the second term. The difference between any two consecutive terms, so it can be the third and the fourth term, the fifth and the fourth one, the 16th and the 15th term, the 100th and the 99th term. It can be any two consecutive term. The difference in the entire progression between two consecutive numbers is the same number. The difference is always the same between two consecutive numbers. That is the most important thing to remember about an arithmetic progression. And for all, n is any natural number. So this n is any natural number, and obviously n is greater than 1. So since there is no such thing as a 0th term, it always starts with the first term, the second term, and so forth. The difference of the two consecutive terms of an arithmetic progression is called the common difference, and the formula, and it is usually denoted by d. So to find any term, this is the formula for it. The first term, a1, plus n minus 1 into the common difference. And how do you find the common difference? This is the formula for the common difference. So an is called the nth term or the general term of the arithmetic progression. So the general form of an arithmetic progression is a1 plus d, And how do we really see what this is? You know that a1 is the first term, a1 plus d will be the second term. So this will be a2. a2, the way to find a2 is a1 plus d. How did we get this a1 plus d? Well, we use this formula. a2 is equal to a1 plus 2 minus 1 into d. 2 minus 1 is 1, so a1 plus d. And we use the same formula for this third term, the fourth term, and so forth. And that's really the most basic introduction for an arithmetic progression. Now we discussed what an arithmetic sequence is in theory. Now let's implement it. With this example, it says here we have to find the first four terms of the following arithmetic sequence. The first four terms are obviously a1, a2, a3, and a4. a1 is already given to us, that's 5. And in this everlasting arithmetic sequence, these three consecutive terms are given to us. Now, we have to find a1, a2, a3, and a4 using this information given. Now, remember that in arithmetic sequence, the common difference, or b, that's the first thing you have to find. So, the common difference is applicable for all consecutive terms. Every consecutive term in the arithmetic sequence, every two consecutive terms in the arithmetic sequence will always have the same common difference. So the difference between 23 and 26 is 3. The difference between 26 and 29 is also 3. So d is equal to 3. The common difference is 3. Now, using this information and the fact that a1 is equal to 5, we have to find a2, a3, and a4. Now, a2 comes after a1, so it is the consecutive term after a1. So a2 is equal to obviously a1 plus d. So 5 plus 3 is equal to 8. That's a2. a3 is the consecutive term after a2. So a3 is equal to a2 plus d. So that's 8 plus 3, and that is 11. a4 is the consecutive term after a3. So a4 is equal to a3 plus d, and that is equal to 11 plus 3, so 14. Now we have a1, a2, a3, and a4. 5, 8, 11, and 14. So these are the first four terms of the sequence given to us. Now we have another question. It says here that a5 is equal to 17 and a9 is equal to 37. Now we have to find the first four terms of the arithmetic sequence. Well, how will we do that? a5 is equal to 17. Now, you must remember the formula that we have for finding a specific term. So that formula is an is equal to a1 plus n minus 1 into d. Now, obviously, what will a5 be equal? a5 will be equal to a1 plus 5 minus 1 into d, which will be equal to a1 plus 4d. And that's what we've done here. So a1 plus 4d is equal to 17. Now, a9 is also given to us. And obviously, a9 will be equal to, what will that be equal to? a1 plus 9 minus 1, which will be equal to 8d. So a1 plus 8d is equal to 37. Now we have two simultaneous equations, and we'll solve them to find the value of d. So when we do that, when we subtract equation 1 from equation 2, we get 4d is equal to 20. So basically subtract these two, and from that you get basically a1 minus a1, that's equal to 0. And basically, basically we'll subtract this equation from this equation. So a1 minus a1 is equal to 0, and 8 minus 4 will be equal to 4d, ad minus 4d, and 37 minus 17 will be equal to 20. So 4d is equal to 20. That's what we have here. So we find the value of d, which is 5. Now that we have the value of d, we can find the first four terms. Simple. When we put d is equal to 5 in equation 1, we get the value of a1. Oh, sorry, it's getting a bit messy here. Now, we've been given that a1 plus 4d is equal to 17. So a1 plus 4 into 5, which is d, and that is equal to 70. Now we have the value of a1, which is equal to minus 3. Now that we have this value of a1, we can just simply find the value of a2 because it is the consecutive term after a1. So a2 is equal to a1 plus d, which is equal to minus 3 plus 5, and that is equal to 2. And we'll have the same procedure for a2, a3, and a4. So that's how you find the four consecutive terms for the first four consecutive terms for this particular example. Now, let's find a specific term in an arithmetic sequence. So the question is, if the fifth term, so basically a5 of an arithmetic progression is 16 and the 20th term, so basically a20 term is 46. What is the 12th term? So basically we have to find a12 when a5 and a20 are given to us. So we remember that the formula to find the common difference is basically an, so we have to find n is equal to a1 plus n minus 1 into the common difference. So when we apply that to a5, we get a1 plus 4d is equal to 16. So we know that a20 is equal to 46. We'll apply the same formula. a1 plus 19d is equal to 46. 19 because it's 20 minus 1 over here. So now that we have these two equations, we'll use the rule of simultaneous equation. We'll subtract the first equation from the second equation. We'll subtract this. And so we get a1 minus a1 becomes 0. So 19d minus 4d becomes 15d. And 46 minus 16 becomes 30. So we have 15d is equal to 30. So d is equal to 2. So we found the common difference. Now, we'll put this common difference in equation 1, this one. And when we do that, we get the value for a1. So a1 is equal to 16 minus 8. And so a1 is equal to 8. Now, the required term is the 12th term. So we know from the formula that that I originally wrote before that a12 is equal to a1 plus 11d. 11 because it's 12 minus 1. And so when we plug in the value of a1 over here, which is 8, and we already know that the common difference is 2, so 8 plus 11 into 2, and that gives you a value of a12 as 30. So now we have to find the term number in an arithmetic sequence. So we have this arithmetic progression, and the three consecutive terms here are 5, 2, and minus 1. So we have to find, is minus 85 in the progression, and what is the term number? So for example, the first term is 5, the second term is 2, and the third term is minus 1. So we have to find the term number from minus 85. And so we've been given these first three terms. So a1 is equal to 5, a2 is equal to 2, and a3 is equal to minus 1. So we already have a1, and d is equal to 2 obviously because, d is equal to minus 3 because 2 minus 5, two consecutive terms, the difference between them is minus 3. And we have to find n. So what will we do here? We know this formula that an is equal to a1 plus n minus 1 into d. So when we apply that over here, we already know that a1 is 5, and we already know that d is minus 3. So an, which is minus 85, is equal to 5 plus n minus 1 into minus 3. So what is n? Well, when you do all the calculations, find out that the value of n is equal to 31. And since this is an integer, we know that minus 85 is in the arithmetic sequence. If this was not an integer, that would mean that it is the minus 85 was not even in the arithmetic sequence. Since it is an integer, it is in the arithmetic sequence, and the term number for minus 85 in the arithmetic sequence is 31. Now, we have to check for the terms in an arithmetic progression. So we have to see if certain terms are actually in an arithmetic sequence given to us. So we must determine whether minus 19 and 2 are the terms of the arithmetic progression, whose first three consecutive terms are 17, 13, and 9. So the rule of thumb is that if we if you actually find out that minus 19 is gives you a term that is an integer, that means that it is in the arithmetic progression, because obviously the term number n must always be a natural number, basically an integer greater than 0. So we have been given the first term, which is 17, and obviously the common difference will be the difference between two consecutive terms, so 13 minus 17, which is minus 4, and the term that has been given to us is 19. We have to verify the value of n and to see if it is an integer or not. So when we already know this formula that an is equal to a1 plus n minus 1 into d. So an, the value that is being given to us is minus 19. We'll plug that in. A1 is 17, so we'll plug that in. And we have to find the value of n, so n minus 1, and the common difference is minus 4. So after doing all the calculations, you find out that the value of n is 40 divided by 4, which is equal to 10. And 10 is an integer, which means that indeed minus 19 is a term in this arithmetic progression. And it is obviously the 10th term. So for the second one, where we have to find 2, so an is equal to 2, d is the same minus 4, and a1 is also the same 17, and we have to find the value of n and check to see if it is an integer or not. So we'll use the same formula, plug in a1 over here, 17, an, what we have to find is 2, we'll plug that in an, and d is equal to minus 4, so we'll plug that in, and we have to find the value of n. So after doing all the calculations, we find out that the value of n is 19 divided by 4, and that is not an integer, which means that 2 is not the term of the given arithmetic progression. It does not exist in the arithmetic progression given to us. So we'll now have an introduction to the arithmetic mean. So let's first discuss what the definition of an arithmetic mean is. So a number a is said to be the arithmetic mean. We'll refer to arithmetic mean as am. So a is said to be the arithmetic mean between the two numbers a and b if a is the term between a and b. So a, so lowercase a, uppercase a, and b, lowercase b, are in arithmetic progression, and the term uppercase a is the arithmetic mean between lowercase a and lowercase b. The middle term of three consecutive terms in an arithmetic progression is the arithmetic mean. So that's simply put, between the extreme terms, if if lowercase a, uppercase a, and lowercase b are in arithmetic progression, then for general purposes, we can say that an is the arithmetic mean between an minus 1 and an plus 1. Obviously, because an minus 1 is the term before an, and an plus 1 is the term after an. So for lowercase a, uppercase a, and b, if we apply the formula, obviously uppercase a minus lowercase a or b minus uppercase a, they're both equal. So when you take a on the other side, take uppercase a on the left hand side and the lowercase a on the right hand side, you get this formula basically. Uppercase a is equal to lowercase a plus lowercase b over 2, basically the mean formula. And for general purposes, an is equal to an minus 1 plus an plus 1 over 2. Now, let's find the arithmetic mean between two values. So we have 3 into under root 5 and 5 minus under root 5. We have to find the arithmetic mean between these two values. So we let a be 3 is equal to 3 into under root 5 and b is equal to 5 into under root 5. So we remember this formula that the arithmetic mean is equal to a plus b over 2. Well, we'll simply put in the values of a and b. And when you do that, this is what you get. So the arithmetic mean between 3 into under root 5 and 5 into under root 5 is 4 into under root 5. Now we have to find the arithmetic mean between x minus 3 and x plus 5. Well, again, you'll put a is equal to x minus 3 and b is equal to x plus 5. So the arithmetic mean is equal to a plus b over 2. We'll plug in the values of a and b. And when you do that, you basically get this value, x plus 1. So x plus 1 is the arithmetic mean between x minus 3 and x plus 5. Now, we have these quadratic expressions, and we'll refer to them as terms. So the first term is 1 minus x plus x squared, and the second term is 1 plus x squared. And we have to find the arithmetic mean between these two terms. So again, we have this formula. We'll plug in the values of a and b. This will be a and this will be b. So when you plug in the values of a and b in this formula and you do all the calculations, you can see that this is what you get, 1 plus x squared. So 1 plus x squared is the arithmetic mean between 1 minus x plus x squared and 1 plus x squared. Now we have to find the four arithmetic means between two numbers. Now remember, an arithmetic mean is not necessarily just one number between two values. It can be many. Basically, what we're trying to find here is that this under root 2 is equal to a1. This 12 over under root 2, it comes after 4 consecutive terms after under root 2. So that will become a6. So basically, if we need to find 4 arithmetic means, this will become a1, and the first arithmetic mean will become capital A1, second will be capital A2, A3, and A4. We have to find these 4 terms, and after that we get A6, which is 12 over under root 2. And the common difference between all of these is obviously the same. So now, we have to find A1, A2, A3, and A4. We've been given these two terms, and obviously under root 2 is equal to A1, and A6 is 12 over under root 2. And when we apply the formula, which is equal to AN is equal to A1 plus N minus 1 into the common difference D. We have to find the common difference. So when you plug in the values, and we have to find the value of D here and do all the calculations, we get that the value of D, the common difference, is 2 over under root 2. Now, simple. Sorry, it is under root 2. So when you do the calculations, obviously A2, we have to find A2, which is equal to capital A1 So the first arithmetic mean that we have to find is equal to A2, and obviously A2 is equal to A1 plus D, and so that becomes under root 2 plus under root 2, which is equal to 2 into under root 2 and capital A2. So the second arithmetic means is the third term, A3, lowercase a3. So that becomes A1 plus 2D, obviously because A1 plus D is the second term, A1 plus 2D is the third term, A1 plus 3D is the fourth term, and so forth. So this becomes 3 into under root 2. We'll apply the same logic for A3 and A4, and we'll get the 4 arithmetic means. Now let's discuss series. So what is a series? Well, it is the sum of an indicated number of terms in a sequence. And what that basically means is that we have this sequence with a common difference of 2. If you replace the commas here with the addition sign, that is a series. So it is the sum of a specific number of terms in a sequence. So the formula to find the sum of the first n terms of an arithmetic series is basically this. Sn is the sum of the first n terms of an arithmetic series. And the formula is n over 2. So the n is the term number. So n over 2 into a1, which is the first term, plus an, which is the last term. And this is another way to write it. So how do we come up with this formula? Well, as you remember, an is equal to a1 plus n minus 1 into the common difference d. When you plug in this instead of this an here, that when you apply it over here, this becomes Sn is equal to n over 2 into a1 plus a1 plus n minus 1 into d. And so when you further simplify it, that becomes n over 2 into 2a1 plus n minus 1 into d. And so that is what you have here. Now we have to find the sum of integral multiples. Now, when you have a question worded like this, you need to see it carefully, what it actually requires. The question says to find the sum of all the integral multiples of 3 between 4 and 97. So the integral multiples of 3, that is basically a sequence or a progression, an arithmetic progression with a common difference of 3, because obviously the multiples of 3 are 3, 6, 9, 12, and so forth. And obviously they have a common difference of, all of them have common difference of 3. So the common difference is 3 between 4 and 97. And it says here that the sum of all of the integral multiples. So that means basically the sum of all of these. What does that basically mean? It obviously means that it is a series. And it says the multiples between 4 and 97. 3 is less than 4, so obviously that is not a part of it. So the first term between 4 and 97, that is the multiple of 3, is 6. So a1 will be 6 over here. See here? And the last number before 97, that is a multiple of 3, is 96. So 96 is the last number. So 6 here is a1, and 96 here is the last number. It's basically an. Okay, so a1 is 6, the difference is 3, and 96 is an. We have to find n. Well, we know this formula. An is equal to a1 plus n minus 1 into d. Put in all these values, and you get the value of n as 31. So 96 is the 31st term in this arithmetic progression. Now we have to find the series. Remember this formula? Well, just plug in the values that you found earlier. So n was 31, a1 was 6, n was 31, obviously, and the common difference was 3. And when you calculate all of this, you find out that the sum of all the integral multiples of 3 between 4 and 97 is 1581. And so that is what you get. So we have to find the terms of a series. So the question is worded like this, that these are the first three terms of the series, -7, -5, and -3, and they amount to 65. So 65 here is Sn, and we have to find n. How will we do that? Well, a1 is obviously -7, so this is my a1 is -7, and the common difference is obviously the difference between two consecutive numbers, and so that means -5 minus -7, and that gives you basically 2. So the common difference d is equal to 2, and Sn, so the sum of the terms that are required is 65, and we have to find the value of n. So how will we do that? Well, you see here that we have this formula, and you remember this formula obviously from the first video of the series. And so basically we'll plug in the values of a1, d, and sn over here, and we have to find the value of n. So when you do that, and when you do all the calculations, you find out that the value of n will be found by solving this quadratic equation. So when you factorize this, you get this equation, and when you do all the further calculations, you find out that you will have two values of n. So either n minus 13 is equal to 0 or n plus 5 is equal to 0. So when n minus 13 is equal to 0, you get n is equal to 13. When n plus 5 is equal to 0, you get n is equal to minus 5. And obviously this n is equal to minus 5 is not possible, because obviously n, as we discussed way back, n must be a natural number. So it must be a positive integer. And minus 5 is not a positive integer. 13 is a positive integer. So that means that this is the correct answer. N is equal to 13. So let's find the sum of the series with xn terms. X can be any constant. So for example, you have this question. These are the terms of the series, and we have to find, and they go to 3n terms. So how will you deal with this? Well, you make groups of 3, and then you make a series with these groups of 3, and they go to n terms because they are 3n terms. If they ask for 2n terms, you would have made groups of 2, and those would go to n terms. So now they ask for 3n terms, so you'll make groups of 3, and they go to n terms. So when you add up these values, you get 1. So that is the first term of the new series. When you add up these values, you get 7. And when you add up these values, you get 13, sorry. And so now you have a1 as 1, this here. And the common difference d is 7 minus 1, which is equal to 6. And n is equal to n because we have to find Sn in terms of n. So how will you do this? Well, you write down the equation, the formula to find Sn, and when you plug in the values, you basically get this. So Sn is equal to n into 3n minus 2, and that's about it really. Now you have to find the series. The given question is that S7, so the sum of the first 7 terms, and S9, so the sum of the first 9 terms, are given like this. Basically, this equation is given. So S9 over S7 is equal to 18 over 11. And A7 is equal to 20. So the 7th term is 20. And we have to find the series. And basically, we'll write down the series in something like this. This is basically the way that you'll write a series, and in this format. So we'll find the first 3 terms of the series and write them down like this, and the dot 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 in front of it. So, well, you've been given this, and you remember the formula that Sn is equal to n by 2 into 2a1 plus n minus 1 into d. So S9 will become 9 by 2 into 2a1 plus 9 minus 1 into d. 9 minus 1 will become 8. So that is what you did here. You replace S9 with this formula equivalent and replace S7 with its formula equivalent as well, which will be this. Now, the 2's here will be cancelled out because, well, obviously they'll be cancelled out. And the remaining terms will be written down like this. And so you'll cross multiply them now. So you'll multiply 11 with this term expression, and you'll multiply 18 with this expression. So this is what you'll get. And when you expand it, you'll get this. And upon further simplification, you get this equation. And when you divide both of these sides by 9, 0 divided by 9 will remain 0. And when you divide this left hand side by 9, you get 3a1 minus 2d. 27 divided by 3 divided by 9 is equal to 3, and 18 divided by 9 is equal to 2. So this is equation 1. So it is also given to us that a7 is equal to 20. And we can write a7 down in its arithmetic progression formula, which is an is equal to a1 plus n minus 1 into d. So a1 is a1, an is given to us as 20, and basically that is a7. So n is equal to 7. 7 minus 1 becomes 6. And we do not have d, so we'll have to find it. So this equation is now given to you. And when you basically take 6d to the right hand side, that becomes 20 minus 60. So a1 is equal to 20 minus 60. And then you'll plug that into equation 1, which is this equation. You replace a1 with 20 minus 60. When you do that, you get this equation. And when you solve it, you find the value of d as 3. Now, when you put d is equal to 3 in equation 1, which is this equation, 3a1 minus 2d is equal to 0. So equation 1 is equal to 3a1 minus 2d is equal to 0. And when you plug the value of d over here, you can find the value of a1, which is 2. Now, you find the second term, a2, which is a1 plus d, and that gives you 5. The third term is a1 plus 2d, and that will give you 8. So now you have the first 3 terms of this series. And so the required series is 2 plus 5 plus 8 plus ... And now this is the answer. Now, let's discuss what a geometric progression or a geometric sequence is. We'll denote it by GP. So, what is a geometric progression? A sequence AN, so any sequence, is a geometric sequence or a geometric progression if AN over AN minus 1 is the same non-zero number for all n is any natural number and basically n is greater than 1. So what does this really mean? Well, it means that if you have 2 consecutive numbers in a geometric progression, and when you basically divide the second number from the first number, it gives you obviously a number, a ratio, and that ratio is consistent throughout the progression. So for example, if you have a1, a2 and a3, basically a2 over a1 is equal to a3 over a2, and if you go on so forth, that means that a4 over a3 and so forth. So the ratio between two consecutive numbers is the same throughout the progression. And that means that the quotient of an over an minus 1, so if we take a2 over a1, basically a2 is an and a1 is obviously an minus 1. So the quotient of an over an minus 1 is usually denoted by r. Remember, in an arithmetic progression, we dealt with the common difference. Over here, we'll deal with the common ratio. The common difference is denoted by d. And so the common ratio will be denoted by r. And so the general term of a geometric progression is given by this formula. An is equal to a1, so the first term, into r, the common ratio, and r to the power n minus 1. So that is the most basic introduction to a geometric progression, and we'll discuss the questions later on. So let's find the fifth term of a geometric progression. So we have to find the fifth term of this geometric progression. Fifth term means basically a5. a1, which is 3, is given to us, a2, which is 6, is given to us, and a3, which is 12, is given to us. We have to find a5. So we have these three terms, and we'll first note down everything we know. a1 is equal to 3. r, the common ratio, is obviously 6 divided by 3 or 12 divided by 6. They have the same common ratio, which is 2. So r is equal to 6 divided by 3, which is equal to 2. And n is 5. We have to find a5. That is unknown to us. So remember the formula. an is equal to a1 into r raised to the power n minus 1. We have to find an. a1 is given to us as 3, r is given to us as 2, and n is given to us as 5. We plug those values in, and when you do that, you basically get 3 into 2 raised to the power 5 minus 1. And when you do all the calculations, you find out that a5 gives you a value of 48. And that is the fifth term of this geometric progression. So now we have to discuss the reciprocal form of a geometric sequence. So this is the question given to us. Show us that the reciprocals of the terms of a geometric sequence a1, a1r square, and a1r to the power 4 form another geometric sequence. So I have to prove this basically. We have been given that this is the geometric sequence. So the reciprocals of these terms, the question asks for the reciprocals of these terms and show that they are also in a geometric progression. And basically the only requirement that a geometric progression has is that it must have a geometric progression must have one value of r, which is the common ratio. So basically, we just have to prove that the common ratio between the first two terms and the common ratio between the next two terms is the same. So this is r and this is also r. So we'll take r for the first two terms. So 1 over a1 r square over 1 over a1 will give you basically this. And now we basically have to prove that, or basically we have to show that the next two terms, so this one and this term, will also give you 1 over r square. If that is true, that means that the reciprocals of these terms are also in a geometric sequence. So when you do 1 over a1 r4, which is this term, so 1 over a1 r to the power 4 over 1 over a1 r square, which is this term. And when you do all the calculations, you basically find out that it also gives you 1 over r square. So the r's, the value of r from both of these calculations is the same. So the reciprocals are indeed in a geometric progression. Now let's insert two geometric means between two numbers. So it says that we have to insert two geometric means between 1 and 8. So basically what that means is, if we just denote the two geometric means as G1 and G2, that would make it four terms. So 1, G1, G2 and 8. So these are all in a geometric progression because the means are also in a geometric progression. So the first term, A1, is 1, and this is the fourth term, 1, 2, 3, 4. This is the fourth term. Oops. Yeah. So A4 is 8. So now what we have to do is, we remember the formula that A1 into Rn minus 1 is equal to An. So when you apply that formula over here, you know that 8 is A4. So A4 is equal to A1 into R raised to the power 4 minus 1, which means A1 into R cube. So A1 into R cube is equal to 8. Using this, we can find the value of R because A1 already given to us, it is 1. So when you put that over here, R cube is equal to 8, and so R is equal to the cube root of 8, which is 2. Now, G1 is equal to A2 as it is the second term in the geometric progression, which is this. G1 is A2, G2 is A3. So A2 is equal to A1 into R raised to the power 2 minus 1, which just means A1 into R. So that would mean 1 into 2, which is R. And that means that G1 is equal to 2. Similarly for G2, G2 is equal to A3. So to find A3, it will become A1 into R raised to the power 3 minus 1, which is equal to 2. So A1 into R square. A1 is 1, R is 2, and 2 square. So 1 into 2 square, which means that G2 is equal to 4. Hence, we found the values of G1 and G2, which are the two geometric means inserted between 1 and 8. Now, let's talk about the sum of n terms in a geometric series and the infinite geometric series. So, the sum of n terms of a geometric series can be found by two formulas. This formula is for the case where the absolute value of r, the common ratio, is less than 1, and this formula is applied when the absolute value of r is greater than 1. So Sn, being the sum of n terms, is equal to a1, which is the first term of the geometric series, into 1 minus r, the common ratio, to the power n, which is the term number. So for example, if you want to find the sum of 3 terms, the value of n would be 3. And this is all divided by 1 minus the common ratio. This is for the case if the absolute value of the common ratio is less than 1. And if the value of the common ratio, the absolute value, is greater than 1, well, we'll have this formula. The only difference between this formula and this formula is in these terms. As you can see, when the absolute value of r is less than 1, this term is equal to 1 minus r to the power n over 1 minus r. And in the case where the absolute value of r is greater than 1, this becomes r to the power n minus 1 over r minus 1. So basically you're just exchanging the positions of 1 and r to the power n and 1 and r. Now, for the case of the infinite geometric series, so that is basically a geometric series which has an infinite number of terms, and so we have to find the sum of those terms. And now you can see that, I mean, just by using common sense, that you can only find this if the absolute value of r is less than 1. Why? Because if the absolute value of the common ratio is greater than 1, that means each consecutive term in the series is becoming bigger. And the value of the infinite geometric series would just be infinity, because the values are getting greater and greater. So if it goes to infinity, that's just infinity. So the sum of the infinite geometric series, obviously the absolute value of r is less than 1, that you can find by this. The first term a1 divided by 1 minus r being the common ratio. So we find the sum of the first 15 terms of a geometric sequence. The question states that we have to find the sum of the first 15 terms, so S15, that is what we have to find, of the geometric sequence 1, 1 over 3, 1 over 9, and so forth. So this is the sequence given to us, and obviously the first term is 1, so A1 is equal to 1, and the common ratio, you can find that by dividing the second term from the first term or the third term from the second term. It doesn't matter because the result will be the same, and that is 1 by 3. And the value of n is obviously 15 because we have to find the sum of the first 15 terms. Now that we have all the data, we know this formula. And since the value of r is, the absolute value of r is less than 1 by 3, sorry, it is less than 1, that means that we have to apply this formula. And when we plug in the value of a1 as 1 and r to the power n, so 1 by 3 to the power 15, and obviously over 1 minus r, and r is 1 by 3. I mean, you calculate that, you get this. And so this is basically the value of S15. Now, we have to find the sum to n terms by converting a non-geometric series into a geometric series. So, the sum to n terms of this series. Now, what we have to do here is, you can see that this is not a geometric series because 33 divided by 3 is equal to 11. But 333 divided by 33 is not equal to 11. So, how do we approach this question? Well, we have to find the sum of n terms, so Sn, of this series. First of all, we'll divide the whole series by 3. So 3 into 1 is 3, so 3 into 11 is 33, 3 into 111 is 333, and so forth till n terms. So now we have this series. But again, this is not a geometric series. So what we'll do now is we'll approach the question like this. Basically, 9 into 1 by 3 is equal to 3. So we'll now replace this 3 by 1 by 3 into 9. We'll take the 1 by 3 common outside and we'll multiply this 9 by this series. So this now becomes a new series, which is this series, and it goes on till n terms. But again, this is not a geometric series. So what we'll do is we'll write down 9 as 10 minus 1, 99 as 100 minus 1, 999 as 1000 minus 1. So basically this goes on till n terms. 10 minus 1, 100 minus 1, 1000 minus 1, 10,000 minus 1, 100,000 minus 1, and so forth. So this is the new series. Now it may be confusing why we have done this, but bear with me, because now we can distribute this series into two different series. this series, in which we take the terms with 10 to the power, so basically this 10, 100,000, 10,000 and so forth, into one term, and we basically write down the ones in another series. And since they are being subtracted, we will have a subtraction sign in the middle. So this is just a series of ones that goes on till n times. So when you add up these ones n times, it just gives you n. And this series now is a geometric series because the common ratio is 10. In the original question, there was no common ratio. Now we have a common ratio. So now what we'll do is we'll basically treat this series, the sum of this series, as n, and we'll apply the sum till n terms, the Sn formula for the absolute value of r is greater than 1 because it's 10. The absolute value of r here is 10. So we'll apply that formula here. And so once you've done that, this is what you'll get. This is what we had to find. A formula to find the sum to n terms of the original series given to us. Now, let's find the sum of an infinite geometric series. So, this is the series given to us, and we have to find, basically, we have to find S infinity. So, first of all, we have the first term, 1 over 5. So, A is equal to 1 over 5. Now, the common ratio, well, you can take the ratio of the second term and the first term, or the third term and the second term. So, basically, just two consecutive terms. And the common ratio just becomes 1 by 5. R is equal to 1 by 5. Now, the important thing to remember is that to find S infinity, the absolute value of R must always be less than 1. And 1 over 5 is indeed less than 1. So we can apply the formula to find S infinity. S infinity is equal to A1 over 1 minus R. A1, which is basically 1 by 5, and R is also 1 by 5. So when you plug in the values, you get 1 by 4 as the answer. So when you add up this series till infinity, there comes a point when the value becomes so small that it becomes negligible. So this is an approximation for the value of S infinity. Now we have to find the sum of an infinite series, and this is a hard question. So we need to find the sum of the infinite series, which is this one. Now, R and K are proper functions, which means that the numerator of the value of R, the power of the numerator of the value of R, is less than the power in the denominator, and same goes for K, as it is a proper function. Now, this is a bit tricky, isn't it? So let's just see what we can do with this. This is what is given to us, and if we multiply the left hand side and the right hand side by 1 minus k, this is what we get. Now you'll see in a second why we did this. When you expand this, you get this series, and you'll notice something about this series. You have terms with just r in them, and you also have terms with rk terms. So you'll convert this into two different series, one with the r terms and one with the rk terms. Now these are geometric series. Why? Because, oh, and also another thing, since the rk terms are actually negative, you just take the negative sign common and make the rk terms positive. So now is a geometric series. Why? Because look over here. This has a common ratio because r squared divided by r is equal to r, and r cubed divided by r squared is also equal to r. So you have a common ratio, which is r. Over here, you can see that r squared k squared, whoops, over r k is equal to r k, and r cube k cube, which is the third term, divided by the second term, which is r square k square, is also equal to r k. So the common ratio is equal to r k. So now we have two geometric series, and so we can apply the formula of S infinity, and that was S infinity is equal to A1 over 1 minus R. And when you apply that on these two geometric series, you get this. So you get this basically. The S infinity for this geometric series is this, because A1 is R, which is the first term, and the common ratio is R, so 1 minus R. And for the second geometric series, you have this, because the first term is RK, so A1 is RK, and R is also RK, which means that it becomes RK over 1 minus RK when you apply this formula. So when you take the LCM of these two, you get this, and when you expand this further, you get this. And so you remember that we multiplied 1 minus k on the left hand side. So what you'll do is, in the numerator on the right hand side, you'll take r common, and then that becomes r into 1 minus k. These two will be cancelled out, and so for S infinity you have this, and this is what we had to find in the question. An expression for S infinity, the sum of the infinite series. This is an interesting bit. You'll use the geometric series on a real world problem. We have to find that a ball is dropped from the height of 27 meters and it rebounds to 2/3 of the distance it falls. If it continues to fall in the same way, what distance will it travel before coming to rest? Because since it's coming to rest, you'd use the infinite geometric series formula. Because obviously it keeps bouncing and bouncing and bouncing, and we do not know how many times it actually bounced. We have no precise calculation for that. So you'll use the formula for S infinity. So the distance traveled in the first fall is 27 meters. So the ball falls 27 meters. And it says here that it rebounds 2/3 of the distance it falls. So when it comes back up, it is basically 2/3 of 27. And obviously it will also come back down in the same length. And then it will go back up to 2/3 of this value. So let's say this value is x. So this is now 2/3 of x. It will come down in the same length and it will go back up to 2/3 of this value, which let's say that 2/3 of x is y. So this is now 2/3 of y. So let's see how we can deal with this. The height of the first rebound is 27 into 2/3. This is the first rebound. As you see, it is 27 into 2/3, which is 18 meters. The height of the second rebound is 2/3 of the first rebound. So It is 2/3 of this 18, and that is 12 meters. So let's see. We write down the first wall as it is, 27 meters, and then you'll add in 2 into this. Over here we've applied the formula of the sum of the infinite series, and obviously this is a bit confusing, because why have we added this, multiplied this 2? Well, because if it goes up, it also comes down. So it covers the distance twice. So it will cover the infinite series twice. Obviously, over here it also goes back, it goes up, and it also comes back down the same distance. So we'll multiply the infinite series with 2. And now to find the infinite series, well, as you know, the first rebound is 18. So 18 is A1. A1. 1 minus R. R, as you know, is 2 by 3, that is given to you in the question. So when you apply the formula and do all the calculations, you find out that the ball travels 135 meters in total. So now we have to find a proof using a given series. So this is the series given to us, and basically we have to show that x is equal to 2 into y minus 1 over y, and we have to prove this using this series that is given to us. So as you can see that this series, because of these dots, it goes on till infinity. So we'll use the sum to infinity formula over here. As you know that a1, which is the first term of the series, is 1, and the common ratio r is equal to x by 2. So we'll use the formula for s infinity. S infinity is equal to a1 divided by 1 minus r, and as you know, from here you can see that y is the sum of this series till infinity. So basically we'll replace s infinity with y, and a1 will be replaced by the first term 1, and r will be replaced by x by 2. So upon doing all these calculations, you can see that we arrive to an equation like this, but we have to make x the subject of this equation. We have to take x on the left hand side. So this is what you get, and hence the proof has been, well, proven. So let's find the deposited amount using a geometric series. So what we'll do here is, a man deposits in a bank rupees 8 in the first year, so this will be the first term of the series, and rupees 24 in the second year, and rupees 72 in the third year, and so on. Find the amount that you will have deposited in the bank by the fifth year. So the deposited amount is given by this series, because the first term is 8, because that's the deposit amount in the first year, 24 in the second year, and 72 in the third year, and so forth. And this is a geometric series. And why? Because there is a common ratio. The common ratio here is basically 3. Whoops. So the first term a1 is 8, and r is 3, the common ratio, and n is 5, because the question asks us to find the amount he will have deposited in the bank by the fifth year. So over here it's asking us that the total amount that he will have deposited in the fifth year. So we don't have to find the term, the fifth term in the series. but rather we have to find the sum of the five of the total amount deposited in the 5 years. So we'll apply this formula here, and as you know, the value of r, the common ratio, is greater than 1. So we'll apply this formula because r is greater than 1. So after replacing a1 with 8, and we'll replace r with 3 and n with 5. So upon doing all this calculation, you'll find that the value comes down to rupees 968. So this man will have deposited a total of 968 rupees in the 5 years. Now let's discuss harmonic progressions or harmonic sequences, and let's do an example where we find the ninth term of a harmonic progression. Now just for simplification, a harmonic progression is just the reciprocal of an arithmetic progression. That's it. And things become very easy once you know this, because we have to find the ninth term of this harmonic sequence. Well, the very first step that you must do is you will convert this harmonic progression into an arithmetic progression, and you'll do that simply by taking the reciprocal of the harmonic progression, because harmonic progression and arithmetic progression are reciprocals of each other. So 1 by 3 becomes 3, 1 by 5 becomes 5, 1 by 7 becomes 7, 1 by x becomes x, and just like that. So once we have this arithmetic progression, you'll use the rules that you would do in an arithmetic progression, how to find the an nth term in an arithmetic progression. So we have to find the ninth term of the harmonic progression. So what we'll do is we'll find the ninth term of this arithmetic progression first. So a1, the first term is 3, so 3 here. The common difference is 5 minus 3, 2. So we have the first term and we have the common difference. So what you'll do is you must find an. So, and the formula to find an is equal to a1 plus n minus 1 into d. So we have to find a9, the ninth term. So we have a1 plus n minus 1, so 9 minus 1 into d, and 9 minus 1 is 8. So a9 is equal to a1 plus 8d. So this comes out to be 3 plus 8 into 2, because d is equal to 2 and a1 is equal to 3. And once we do the calculations, you'll find that 19 is the answer. But this is not the complete answer, because this is where people start making mistakes. The question asked us to find the ninth term in the harmonic sequence. This is the ninth term in the arithmetic sequence. We have to convert this back into the harmonic sequence, and how you'll do that? Well, you'll take the reciprocal. And so the ninth term of the harmonic progression is 1 by 19, and 19 is the ninth term of the arithmetic progression. Now we have to find the harmonic means, and we'll see how to do this by a question. The question says we have to find 5 harmonic means between the two given terms or two given numbers, minus 2 by 5 and 2 by 13. So this comes down to a total of 7 terms, because this is the first term, and then we have the 5 harmonic means, and then we have this as the last term, and so this will be the 7th term. So let a1, a2, a3, a4 and a5 be the arithmetic means. This is very crucial. It says that these are the arithmetic means between minus 5 by 2 and 13 by 2. Why are we taking these numbers? Because they are the reciprocals of these numbers. The reciprocal of minus 2 by 5 is minus 5 by 2, and 2 by 13 is 13 by 2. And as you know, the reciprocal of a harmonic mean
is an arithmetic the reciprocal of a harmonic progression is an arithmetic progression, and the reciprocal of an arithmetic progression is a harmonic progression. So that's why we have done this. We will treat this as an arithmetic mean for the while, and then we'll convert it back to a harmonic progression later on at the end. So we have this arithmetic progression over here, 7 terms, and so the first term a1 is minus 5 by 2 and a7 is 13 by 2. Well, simple. So how we have to find basically the value of d, the common difference, because only by finding out the value of d will we be able to find the values of these 5 means, and in turn the harmonic means. So a1 plus 6d is equal to a7. Obviously, you remember this formula that an is equal to a1 plus n minus 1 into d. So a7 is equal to a1 plus 6d, and that's what we've done here. a1 plus 6d is equal to a7, and a7 is given to us as 13 by 2. And also this a1, that is also given to us as minus 5 by 2. So this now becomes minus 5 by 2 plus 6d is equal to 13 by 2. So we can now find the value of d, and that comes down to 3 by 2. And now the question becomes very simple. a1, which is the second term of the progression, because the first term a1, the lowercase a1, that was minus 5 by 2, and the first arithmetic mean, capital A1, that is what we have to find. That is the second term of the progression. So a2 is equal to a1 plus d, or a1 plus n minus 1 into d, and n is equal to 1, sorry, n is equal to 2, so this simply becomes a1 plus d. So this comes down to minus 1, and the reciprocal of minus 1 is minus 1, so the first harmonic mean is minus 1. And we'll use the same logic for all the other means. a2 is equal to lowercase a3, as it is the third term of the progression, and that is equal to a1 plus 2d. And when you solve this, you find out that a2 is equal to, this a2 is equal to 1 by 2, and its harmonic equivalent will be its reciprocal, which is 2, and so on. You will find the value of a3, a4, and a5. So you now have these 5 harmonic means, and now the required harmonic means are minus 1, 2, 1 by 2, 2 by 7, and 1 by 5. And so you solve the question, and now you know how to find harmonic means. Now let's see how we can find an unknown value using a harmonic sequence. So if the numbers 1 by k, 1 by 2k plus 1, and 1 by 4k minus 1, if these numbers are in an harmonic sequence, find k. Now you might be thinking, well, how do we really approach this question? Because you can think of many things. There are so many formulas, so many strategies, but in this particular case, things are very simple, because as you know, in the very first step in solving a question with a harmonic progression is to convert it into an arithmetic progression, and that we can do by taking the reciprocals of every term. So 1 by k becomes k, this becomes 2k plus 1, and this becomes 4k minus 1, and this is the equivalent arithmetic progression. So as you know, the common difference is common, so d is the common difference, and basically the common difference is the difference between two consecutive terms. So the value for d, the difference between the second term and the first term, is equal to the difference between the third term and the second term, and that is equal to the difference between the fourth term and the third term. It is the same. The common difference remains the same. That is why it is the common difference. So we'll just use this logic. So 2k plus 1 minus k, that is equal to 4k minus 1 minus 2k plus 1. And by using this, you can find out the value for k. It's as simple as that. Once you solve this, you see that the value of k is 3, and that is all you need to do in this question. That's it. Now, let's see the use of geometric and harmonic means. If the positive geometric and harmonic mean between two numbers, let's suppose these two numbers are a and b. If the geometric mean is 4 and the harmonic mean is 16 by 5, find the numbers, find a and b. That's the question. So, let a and b be the required numbers, and then these are the conditions given to us. As you know, the under root of the two terms is the formula for finding the geometric mean. So the under root of a and ab is 4. And if you take the square on both sides, ab becomes 16. So we now know that the formula to calculate the harmonic mean is 2ab over a plus b. Remember this, 2ab over a plus b. And this is given to us as 16 by 5. And if you cross multiply these sides, you get this equation, and we'll regard this equation as equation number 2. So from equation number 1, which is this one, you can see that a is equal to 16 by b when you take b on this side. A is equal to 16 by b, and we'll regard this as equation number 3. And now we'll put this equation number 3 in equation number 2. So we'll replace a with 16 by b. So this is what you get. And now using this equation we can find the value of b. But it's not really that simple, because this comes out to be a quadratic equation. So you'll have two different values of b. So after doing the factorization of this quadratic equation, it comes down to this. And so you get two values for b, 2 and 8, because either b minus 2 is equal to 0 or b minus 8 is equal to 0. So when b minus 2 is equal to 0, the value of b is 2, and when b minus 8 is equal to 0, the value of b is 8. So when you put b is equal to 2 in equation number 3, now what was equation number 3? This is equation number 3, and now you'll put the value of b in it to find the value of a. So once you do that, you can see that when you plug in the value b is equal to 2 in that equation, you get the value of a as 8. And when you plug in the value of b is equal to 8 in this equation, you can see that the value of a is 2. So the required numbers are 2 and 8 or 8 and 2. The value of a can either be 2 and 8, or the value of b can be either 8 and 2. But if the value of a is 2, the value of b is 8. If the value of a is 8, the value of b is 2. And so that's how you do this question. So let's discuss the definition of sigma notation, or as in other words, the summation notation. So the sigma notation is represented by this Greek letter, and it is used to denote sums of different types. So basically, if we have this example, we have this particular example here. Now, what does this mean exactly? It is used to express the sum, and what we mean by that is that if there is a series, a sum basically, that goes from am plus 1. So basically am is the first term, am plus 1 is the second term, am plus 2 is the third term, and so forth till an. Then the sum expression, so let's just say that am is 1, am plus 1 is 3, am plus 2 is 5, and so forth till n terms, that can be written down like this, because this particular summation is represented like this, and that is just a general way of representing the summation notation. If we take this example here, that can be written down like this. And basically, 2k minus 1 is the kth term of the sum, and k is called the index of summation. And as you can see, k is equal to 1 and n over here. So 1 and n are called the lower limit and upper limit of the summation. So basically, k is equal to 1 and it goes on till k is equal to n. And that is how you represent this particular summation notation. These are odd numbers, and obviously odd numbers can be represented by this particular expression over here. And k goes from 1 till n, because that is the total number that we have to find. So formula for the sums. As we know that this particular example here, in this particular case, k goes from 1 till n, and that is equal to n. Why? Because it's just 1 being added up n times, from 1 time till n times, and obviously that just gives you n. And see this example here, this is the one we did previously, and this is the sum of odd numbers, this is the sum of natural numbers starting from 1 till n, and that can be represented by this particular notation. And obviously you can see that k goes from 1 till n. So when k is equal to 2, this becomes 2, and that just equals 1 plus 2 plus 3 plus so forth till n over here. And that can be represented by this. So basically this summation is equal to n into n plus 1 over 2. And so the sum of square of the first n natural numbers is equal to this. So this is 1 square plus 2 square plus 3 square plus 4 square, blah 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 blah, till n square. And obviously that is equal to this particular notation, because the value of k is now k square, and that can be that is equal to, the summation is equal to this expression over here, n into n plus 1 into 2n plus 1 over 6. So now we look at the sum of the cube of the first n natural numbers, and this goes on 1 cube plus 2 cube plus 3 cube plus 4 cube and so forth till n cube. And that can be represented obviously by this, as k is now k cube. And this is basically represented by taking the square of the summation of the natural number, this here. If you take the square of this expression over here, you get the sum of the cube of the first n natural numbers. And that's it. You have to remember these three in particular, because these three are used consistently in questions that we will do later on. So let's find the sum of the series by using summation. This is the series given to us, and we'll deal with it in two separate ways, because we can use these addition signs as separators. So we now have 1 into 4, 2 into 7, 3 into 10, and so forth. Now you'll deal with these terms differently, and you'll deal with these terms differently. So how do we go about this? Well, the term to find an of 1, 2, 3 and so forth is n, obviously, because when n is equal to 1, so a1 is 1, the first term, a2 is 2, the second term, a3 is 3, the third term. So basically this just goes on till n. And you see this, the term, the expression for an in this particular case, you can find by the formula for arithmetic progression, because this has a common difference of 3. 7 minus 4 is 3, 10 minus 7 is 3 and so forth. So you see you remember the formula for calculating an in an arithmetic sequence, and that was a1 plus n minus 1 into d. And in this particular case, a1 is 4, the first term of this sequence, and n is a constant here because we have to find an expression for n over here. So n will remain n, and d, the common difference, is 3. So that is what this comes out to be, 4 plus n minus 1 into 3. And in the end, this comes out to be 3n plus 1. So 3n plus 1 is equal to an. And now, because the question asks us to find an expression for the sum of this series, you will multiply these two terms, these two expressions for an, because over here it is being multiplied. These two terms are being multiplied. So this comes out to be n into 3n plus 1. This n and this 3n plus 1 will be multiplied, and then you'll get 3n square plus n. And now this, if you replace the n's with k, you get an expression for tk. This is basically equivalent to just the k, or the index. So we have to find Sn for this. So what do we do here? Over here, Sn is equal to T1 plus T2 plus T3 plus T4 plus so forth till Tn. And that can be put in this summation notation. So Tk from k is equal to 1 till k is equal to n. And then we have to find an expression, the final expression for Sn. And how do we do that? Well, you remember that Tk was equal to 3k square plus k. And now you can basically, this summation can be applied on 3k square and k differently, separately, and they will be added. So this is what you'll do. This summation notation will be used on 3k square, and then it will be added on the same summation notation on k. And now over here you can take this 3 outside because it is a constant. So this 3 will go outside, and now you have expressions of summation for k square and k. And you remember that we discussed the formula of the sums. You will just replace these expressions with those formulae that we discussed earlier, and now you'll just simplify this. So this 3 over here, this will be cancelled with this 6. This 6 will become 2, and so you get this. Now the 2 is a common denominator in both, so they can be added, and upon addition you get this, because this n into n plus 1, this term is common in both of these expressions. So now you have n into n plus 1 over 2 into 2n plus 2. And upon further simplification, this is what you get. This expression is equal to Sn, and that is what the question required us to do. So the sum of the series by using the nth term. Now this is the series given to us, and in this particular case we have these consecutive negative and positive signs, and that is what makes this a bit confusing. 1 square minus 2 square plus 3 square minus 4 square plus 5 square minus 6 square, and so forth till 2n minus 1 whole square minus 2n square. So how do we deal with this? Well, you see that this series over here, it goes on till 2n minus 1 whole square minus 2n square. So that makes things a bit simple for us, because that means that Tn is simply 2n minus 1 whole square minus 2n square. So when you actually expand this, this gives you the value minus 4n plus 1. So Tk is equal to minus 4k plus 1, since Tn is equal to minus 4n plus 1. And now you'll use the summation notation to find S, and that is what the question requires, the sum of the series. So Sn is equal to T1 plus T2 plus T3 plus T4 and so forth till Tn. And so this now becomes the summation from k is equal to 1 to k is equal to n of Tk. And now you'll simply replace Tk with minus 4k plus 1, and you'll deal with minus 4k separately and 1 separately. So basically you'll apply this summation on minus 4k, and then you'll add it into this same summation on 1. And so you'll take this minus 4 outside as it is a constant, and this becomes minus 4 summation of k, and this is just summation of 1 because there is no other constant over here. And so now this becomes minus 4 into the summation of k, and as you remember from the sum formula that we discussed, this turns out to be n into n plus 1 over 2 plus the summation of 1, which is simply n, as 1 is being added up n times. So now you'll basically just simplify this expression, and so that gives you this quadratic equation, and this is the expression for Sn. Whoops. Just a second. Yeah, this is the final expression for Sn. This is more simplified. And you can even further simplify this actually. And yes, this turns out to be minus n into 2n plus 1. And that is equal to Sn.